It's my great pleasure to introduce you Professor Asuman Aksoy from Claremont McKenna College. And she's going to talk about backward shifts have gone nuclear. Asuman, please.
Right. Well, thank you. Well, I want to start thanking Jawad and the other organizers for giving the opportunity to present this work here. And I also want to thank Zahra for consistently sending all the information to us. As you see, my title is Backward Shifts Have Gone Nuclear. And this is what I'm going to talk obviously about. But I am taking a slightly different approach because this topic maybe not exactly in the main theme of this workshop. So I thought it will be better if I try to give a little bit of history. As you know, every problem in mathematics has a history which creates its story, and that is the reason for why some of us have motivation to solve problems. So I will try to convey those kind of story related with backward shifts, why they go nuclear. And in the process, I'm going to insert human faces. The first face you are seeing here is my co-author, my collaborator, Uniet Puig. Uniet is visiting professor now at Claremont McKenna College, where I've been forever. Okay, the CMC stands for Claremont McKenna College. Okay, here is the talk map. This is my plan. After setting notations and going over preliminaries, I'm going to concentrate on a particular factorization theorem for compact maps. I'm sure many of you heard about other factorization theorems such as Johnson's for compact maps, but the one I'm going to talk is maybe lesser known, which turns out to be very useful, not just for our purposes, but for in other areas as well. So after I explain what that factorization theorem is about, I'm gonna change gears. I'm going to introduce hypercyclic operators, which are not compact. So you can say, oh, you just mentioned the factorization theorem for compact maps, and now you are giving this hypercyclic operators, which are not compact. Well, nevertheless, yes, that is true. Nevertheless, by looking at factorization for compact maps, one can get some mileage in understanding hypercyclic operators. And using backward shifts, I'm going to define the operator ideal. So I will define what operator ideal is. And this particular operator ideal, WPQ backward nuclear operators. As you see, it's a mouthful. So from now on, whenever I say backward nuclear operators, I am talking about WPQ backward nuclear operators, but I'm not going to say that. So using backward shifts, I will present a theorem which tells how you can factor operators, this kind of operators. And then, of course, the question is, what kind of consequences this factorization will give you? I will mention some, and I also will mention some of the questions. So that's my talk map. So let's start with the preliminaries. As usual, by LXY, I mean the norm vector space of all continuous functions from X to Y. And when we put K, that is
Sorry to interrupt, Asuman. I just see the front page backward shift. Do you proceed?
Oh, yeah. You are not seeing it?
I'm just seeing backward shift have gone nuclear.
Okay, I'm going to stop sharing and then come back.
Yeah.
Do you see a different
yeah,
page now?
it works. It works now.
Okay, thank you.
I missed the photo. I'll get you. I mean,
All right, then
awesome.
I will go back.
Okay, I see it now.
This is Uniette. This is my collaborator. This is my talk map. Thank you for warning. So, you know, and sorry about that. I don't know why it stopped. All right, and now too much. Okay, so I'm setting my notation. LXY is what it is, and KXY is the collection of compact operators from X to Y. U sub X unit ball, X star is the dual space of X, and when I write A cross Y, I mean the usual rank 1 operator. So A cross Y of X is A of X, Y. When I use P prime, I mean the conjugate exponent of P. So 1 over P plus 1 over P prime is equal to 1. And LP of I denotes the Banach space of all absolutely P-summable scalar families. Okay, so these are the standard notations. Now here, the story of compact operators starts with this master, which doesn't need any introduction, Alexander Grothendieck. Well, here I put 3 pictures from 3 different periods of his life. And in the first one, when he wanted to save the world, you know, as you know, he was very socially conscious person. In the second one, I guess he was solving difficult problems in math. And then this last picture is when he was really reclusive towards the end of his life, when he was in the mountains in France. But the connection to what I'm going to talk with Grothendieck is lies in this resume or in his thesis, which goes back to 1956. And apparently what I read, that thesis was quite hard to understand, and results in it remained a mystery for mathematical communities quite a long time. And in 1968, Lindenstrauss and Pelczynski cracked it, and they published this result that he has, which is a characterization of relatively compact set. A subset K in a Banach space X is relatively compact if it is contained in the closed convex hull of a norm null sequence. So here xn's, norm of xn's are going 0, and here alpha n's in absolute value less than or equal to 1. See, this turns out to be a very useful characterization of compact sets. And of course, if you have this characterization for compact sets, you can say what is the T of unit ball of X is going to be contained in, using the fact that T being compact means takes bounded sets into relatively compact sets. So T unit ball of X is going to be contained in closed convex hull of alpha and YNs, and now YNs are norm null sequences. Okay, this is the characterization by Grothendieck. Now, maybe I don't need to tell you this, but let's do it for the sake of completeness. I want to define what I mean by weakly p-summable sequences and weak star p-summable sequences, because they play quite an important role in the factorization. So weakly p-summable sequences, which the notation is W for weakly and P. And so a sequence is going to qualify to be a member of this space if and only if A of xi is going to be in LP for all linear functionals in X star. So what that means is then this sequence, you can look at LP norm of that sequence and then take supremum over all A when norm of A is less or equal to 1, then you have a Banach space, okay? And that Banach space is weakly p-summable sequences. And the dual concept is the weak star p-summable sequences. And again, here, this makes it clear. These are the weak star p-summable sequences in X star, and a sequence of linear functionals is going to qualify to be in the LP W star X star if and only if AI of X is going to be an LP. So do the same thing, find the LP norm and take the supremum over all X, where norm of X is less than or equal to 1. Then you get these weakly p-summable sequences. Okay. What is interesting about this sequences, there's a lot of things that are interesting if you look at Jarkov and Pelchinsky's book. But for my purposes, that there is an isometric identification of these spaces with the space of bounded linear operators. In case of weakly summable sequences in X, this space, this Banach space, can be identified isometrically with the bounded linear operators from LP prime to X. And I did put here in case, you wanted to be reminded how you can do this identification. And weak star p-summable sequences on X star can be identified with the bounded linear operators from X to LP. So either from some LP space into X or from X to LP, these weak and weak star summable sequences are quite useful. Okay, now I said I'm gonna change, shift gears a couple times, and now I'm doing that. So I am showing you the picture of my undergraduate advisor, Tosun Terzioğlu, who passed away in 2016. And, there was a conference for him and his contribution. So, I wanted to go to that conference, and I wanted to understand what kind of, print that Tosun left to mathematics. And I come across with this paper. And the paper is a characterization of compact linear mappings. And that's published in 1971. So it's quite a nice work. And I didn't realize the consequences of this work of Tosun. Okay. Here is his theorem. Here is his factorization. This is a factorization theorem for compact operators. So T, and it has equivalences of 3 items. T is compact. Then the normal, there exists a normal sequence, X and star in the dual, such that you can find an upper bound for the norm of T of X's. So that upper bound in terms of a normal sequence. And there is a closed subspace of C0 where you can factor your compact operators. So you can find P and Q. P is compact from X to Z, and Q is compact from Z to Y, such that Q composed by P gives you T, and the Z I'm talking about a closed subspace of C0. So this equivalence of 3 conditions is his main theorem. And when I looked at the proof, I realized that he uses heavily Schauder's theorem. T is compact if and only if T star is compact. And then I looked at what kind of, results this theorem produced. Again, I come across with several papers, and actually I have written a paper about the consequences of this theorem. And, but I guess in a short time, what I can say is that if T is an operator from X to Y, and you extend this operator, and as usual, let's call the extended operator T tilde. If T is compact, what can you say about T tilde to its extension? And if the norm of T tilde is less or equal to some lambda times norm of T, there are certain spaces, if your space X has that property, they are called P lambda spaces. And again, several people looked at these P lambda spaces, and they understood that those spaces have approximation property, which then, produce some other results. using Tosun's theorem about factorization. Okay, so the one particular factorization is this, and here I have equivalence of all of these three conditions. Now, let's get into the hypercyclic operators. Let me start with the definition, and then I will explain hopefully a little better. A bounded linear operator acting on a separable infinite dimensional Banach space X is called hypercyclic if you can find an X in X such that Tn of X is dense in X. So what this says, X, Tx, T squared X, and so on. In other words, the orbit is going to be dense in X. So what are the examples of such operators? Well, translations and differentiation operators on the space of entire functions are hypercyclic. But if you ask the question, how do you prove an operator is hypercyclic? It seems like this very definition is not the one you should usually go. And over time, the people who are working in this area develop certain criteria to show certain operators hypercyclic, okay? But one prototype of hypercyclic operator, which I am very much interested, is the backward shifts on L2 of n. And that was first identified by this nice man, Stefan Rolowicz, this Polish mathematician. He showed that if you consider backward shift operator and multiply that with some constant lambda, so if you look at lambda b, taking the sequence xn to lambda xn plus 1, this is hypercyclic for any scalar where absolute lambda is larger than 1. So his example was lambda 2, and I think he considered also this kind of operators on fresh spaces. So this is a typical example of a hypercyclic operator. And if you just look at the backward shift, that's not hypercyclic because the norm is 1. But if you have a hypercyclic operator, norm of t is going to be larger than 1. Well, here I list some basic properties of hypercyclic operators. I'm not an expert on hypercyclic operators at all, but if you look at standard books on hypercyclic operators, these properties come immediately in the very first chapters. And there are results some people call automatic hypercyclicity, which means every power of a hypercyclic operator is hypercyclic. That seems to be used a lot. But infinite dimension on the space X is required. It seems like hypercyclicity purely an infinite dimensional phenomena. And no compact operator on complex or real Banach space can be hypercyclic. So I'm going to come this item again, so I will explain that a little better, I hope. And the existence of hypercyclic operators are at a separable infinite dimensional Banach space admits a bounded hypercyclic operator. And the last one here is, again, I'm coming back to the backward shift. It's due to Salas, which appeared in the transactions of AMS in mid-90s. And this result of Salas emphasized the role backward shifts plays in terms of their weight sequences. Okay, hypercyclic operators are not compact, and why is that? It is because a property of its spectrum. See, if I have a hypercyclic operator, and if I look at the spectrum of that, then there is a theorem which says that every connected component of the spectrum of that operator intersects the unit circle. So if you have an infinite dimensional Banach space And if your operator is compact, then the point spectrum is countable and contains 0, right? And that is the connected component of the spectrum of T, so it violates this theorem. So no compact operators on a complex Banach space or real Banach space X could be hypercyclic. Then where is the connection? And I will explain the connection in a minute, because I did start it by saying, oh, there is this particular factorization of compact maps. Then I said, oh, here are hypercyclic operators, and the backward shift is one particular one. And then I didn't, connect those two things yet. And if you want to know more about hypercyclicity, there are two excellent texts written about it. One is Materon's and Bayard's things. It's about dynamics of linear operators. That is from Cambridge Tracks in Mathematics. And Gross Erdmann and Alfred Paris also has written, and their title of their books is Linear Chaos. And that's from Springer. And the first book is maybe more technical, maybe for more advanced line. But the second one is also contains a lot of good results, but has a lot of examples. So I found that quite useful. Okay, here is my first attempt to make a connection. I mean, it's not clear, that connection, still is not clear, to tell you that if I look at weighted backward shifts, I can write it as a T of unit ball of X contained in some set which looks similar like what Grothendieck's characterization of relatively weakly compact sets. So we are interested in studying operators satisfying this condition, okay? So, but here, what I have here, alpha n's are in the unit ball of LQ prime, and YNs are, they are not normal sequences, but they are weakly Q-summable sequences in X. And these operators can be hypercyclic. In fact, the weighted backward shifts satisfy this. When I come to that point, I will write my weighted backward shift in relation to this. Okay, here is another human face to these ideas. And that's a picture that I taken during a conference in Trier some years ago. And this is Albert Pitch, okay? Since I used his book a lot, and you see this is library's copy, but it's been staying with me for years. It's okay, nobody called back yet, so I guess it's okay to keep it this long. I feel a little bit of guilty, but that's okay. Okay, well, this is a subject, operator ideals, and it seems like it sits in the intersection of operator theory with other areas, classical areas of functional analysis. This book is almost contains an encyclopedic knowledge, and I always have difficulty pronouncing that in English, so I'm just gonna say it in Turkish. Encyclopedic knowledge of the operator ideals. And it's an old book, so there has been some progress in this field. And if you are wondering about the new progress, that you gotta go and look at Handbook of Geometry of Banach Spaces, Volume 1. There is a rather long article, and Peach is one of the authors of that article, which also explains the recent progress. So what is this operator ideals? Well, an ideal of operators between Banach spaces is an assignment U, which associates to every pair of Banach spaces X and Y a subset of LXY, so U is same as UXY, which is a subset of LXY, such that the following conditions are held. So it's a closed subspace actually of L of xy containing all finite rank operators. As you see, that condition 1 tells you that. Condition 2 tells you that it's closed under summation. So if I have T1 and T2 in this operator ideal, T1 plus T2 is there. And the last one is probably the most important property of an operator ideal because it's the ideal property. So T is in this operator ideal. A and B are bounded linear operators. So if I have T in going from X to Y in this operator ideal, then, for the Banach spaces X naught and Y naught, if I form the BEPs A and B, A is going from X naught to X and B is going from Y to Y naught, then this composition, which here I put as BTA, gets into the operator ideal. So that's what I mean. This is an operator ideal. Well, what are the examples? Finite rank operators, for example, is the smallest operator ideal that you can look. So how do you work with this structure? Well, you put an ideal norm on it, and the ideal norm, so then U with this norm becomes a norm space, and it does satisfy these two conditions. Here it says alpha of norm 1 operators is going to be operator norm of X star and operator norm of Y. I mean, norm, just not the operator norm, sorry, for all X star and X star and for all Y and Y. And if you look at alpha of that composition, A and B, now they are the operator norm, but here T was in the ideal, so that's the ideal norm. So if I look at this pair U alpha, I get an operator ideal. Okay, so these are operator ideals. Now, what are the examples of operator ideals? Compact operators are ideals of compact operators is an operator ideal, and also nuclear operators. Okay, an operator from X to Y is called nuclear. I heard that some of the people who presented in this workshop did say something about nuclear operators. So perhaps it's not, that outside, but I guess the nuclear operators were first introduced by von Neumann, because he was asking what questions on Hilbert space have well-defined traces. And they called these operators trace class operators. But Grothendieck again, Master Grothendieck again, is the one who, extended these ideas to Banach space setting. And then T from X to Y is called nuclear if it has this nuclear representation. Okay, look, I'm writing this as summation of rank 1 operators where AI is in X star and YI is in Y, such that norm of AI multiplied with norm of YI is finite. And then you can look at all possible representation, take the infimum of it, and define a norm on this operator ideal. So this is what we call nuclear norm. And this T being able to written like this is what we call nuclear representation. Okay. So as I said, Grothendieck not only defined these concepts for in the context of Banach spaces, he did give a factorization for nuclear operators through a diagonal operator from L infinity to L1. So this kind of diagonal operators from L infinity to L1 are prototypes of one nuclear operators. So later, by exchanging this L1 with LP spaces, there is, the class of p nuclear operators are defined, and there is, quite a bit work on it. But the type of nuclearity I'm going to define is going to be different than this one, but very similar in some sense. Now, before I go to the weighted shift and how that can be used in factoring backward nuclear operators, I want to give you some justification that, weighted backward shifts is a favorite testing ground for operator theorists. For example, there is a rather recent result of He, Huang, and Yu. They show that if X is a Banach space and En is a basis, and if a weighted backward shift admits an orbit with a non-zero limit point, then BW is hypercyclic. And I mentioned Salas's result, but Salas has quite a large number of results in this thing of characterizing hypercyclic forward weighted shifts in terms of their weight sequences. So I guess what I'm trying to say is that this is a testing ground for people in linear dynamics, but not only people in linear dynamics. And I just couldn't resist to put the picture of one of my teachers many years ago, another nice man and good mathematician, Alan Shields. And as you guys know, he also used weighted shifts in analytic function theory. Okay, so now finally, after all this, background, I guess I'm ready to ask the question, can one use backward shifts to obtain factorization of hypercyclic operators? And the answer is yes. And you can do this actually if you can show that an operator ideal gets into the picture. Okay, so now I'm defining what I call WPQ backward nuclear operators. These are not nuclear operators. So what is the difference is? Difference is you have a weight here. You have AI tensor y I minus 1. So that is shifted, okay? By shifting this, this is no longer compact, okay? And, but here, AIs are weak star summable sequences and YIs are weakly summable sequences. And I made a point of, at the beginning, telling you that this space can be identified with the space of bounded linear operators, and so is this space between appropriate spaces, obviously. Here, W is a weight in L infinity. So this is backward nuclear, and this is the backward nuclear representation. Okay, then again, I look at all such representations and then take infimum over. Well, AIs were weak star summable sequences, so take their weak star summable norm and YIs, respectively, weakly norm, and this was in L infinity, and take infimum over all possible representations. Then you get this norm. Okay, so the notation now is justified backward because y minus 1, nuclear WPQ, and this is the notation that I'm going to use for backward nuclear operators. So the question is, can you find an example for such an operator? Yeah, weighted backward shifts are an example of such operators. Okay, so here what I'm defining is just repeating what I mean by weighted backward shifts. Okay, but maybe this is a better representation. Here I'm writing backward shift as summation WI EI star EI minus 1. This is weak star summable, and these are weak summable sequences. Okay, so I can write this as a backward WPQ backward nuclear operators from LQ prime to LP. Okay, So, okay, good. So you have an example and you define something, but is this an operator ideal? And this question is very technical, and I'm not going to present the proof of it, but this is the one which cracks the factorization, and that is the easier one, which I will present to you. So we did show that this is an operator ideal. So we answered the question in affirmative. So if I look at backward nuclear operators with the norm that I define, that is going to be a S-Banach operator ideal. Okay, don't worry too much about that S. What that S is that in the properties of the norm, when you are writing S is first of all between 0 and 1, it could be 1. When it's 1, there is no difference than the operator ideal. So actually, we are proving something little more, than just operator ideal. So this depends on several criteria. So this becomes an operator ideal. Okay. If it's your operator ideal, then show me a factorization of this. And well, this is our theorem, which says that T is a bounded linear map between X and Y. And then here is your backward shift from LQ prime to LP. It's unilateral backward shift. Then the following are equivalent. This becomes a backward nuclear operator from X to Y if you can find S and R such that you can write this. And moreover, you can, write the norm in the space. Okay, if I repeat what I said in this theorem, what I'm trying to tell you that T gets into this operator ideal if T admits this factorization. Okay, and so how do we do this factorization is obviously, contained in the proof of this. But here, if because I have the chart here, if I just tell you that there is an easy way to look at S by taking an X and sending to AI of X here, and take a sequence nu I in LP, and R is nu I, yi ends up in Y. And if I do this properly, because I had equivalence of two statements, one statement is T is backward nuclear, show me the factorization, and I kind of give an idea about that. And the other one is, suppose you have the factorization, show me that you have the representation for backward nuclear operators. And the first one is, suppose, it's a backward nuclear operator, then it has this representation. And because norm satisfies this property, by defining R and S and realizing that operator norm of S is the weak star norm of AIs, and operator norm of I is the weak norm of YIs in LP prime, does the job. Okay, so that will give. The other way around uses the full swing of the power that we are dealing with an operator ideal, because as I wrote before, I can write BW in this form as a backward nuclear operators LQ prime to LP, where this norm is less than or equal to L infinity norm of the weight, which is same as norm of BW. So because it's an operator ideal, I can, have a map from X to Y. Remember that third property of operator ideals, that does the job. Okay, so there is this factorization. Then I guess the question is, okay, it's fine, you factored it, but you still did not tell us what is the connection to compact-like, operators. And that's coming. Okay, so let's go. Now here, when you have an operator ideal, okay, the usual thing is to look at its injective and surjective halves of that operator ideal, because there is a duality theory between injective and surjective halves. And an operator ideal is injective if it's equal to its injective half. That happens if your Y target space has the extension property, and an operator ideal U is called surjective if it's equal to its surjective half, and this happens when X has the lifting property. So for example, the ideal of finite rank and compact bonds are both injective and surjective. So since we had this operator ideal, the natural next step was to look at its injective and surjective halves of it. And when we looked at its surjective half, and we have results about its injective half as well, but I'm not going to present those here, because the point I'm trying to make is that the Terzioğlu's type of characterization of T of unit ball of X can be achieved when you have his kind of factorization for backward nuclear operators. So here is the theorem, the second theorem that I'm presenting. T is a bounded linear map from X to Y, and BW is a linear map from LQ prime to LP, is a unilateral backward shift. Then T being in the surjective half is equivalent of being able to find an operator P from LQ prime to Y, but this operator P is special. Okay, special in the sense that you can write this as a summation of the ingredients, what I say, okay, not just alpha I yi's, but xi plus 1, wi plus 1 yi's, because we introduced a weight into the nuclearity, such that T of x is contained in this thing. So where, xn's are coming from unit ball of LQ prime. So what this says is, yes, your hypercyclic operators are not compact because of their property of one particular hypercyclic operator, backward shift, being contained, can be written in some sense, Grothendieck type of criteria makes this result more interesting. There is a symmetry that's going on here. And that symmetry is identified even more if you look at the dual of this injective and surjective hull of this operator ideal. I mean, here I just put one, there's a symmetric argument here. Here I'm taking dual of the injective hull and I'm getting surjective hull. But you can start with the surjective hull and take its dual, get the injective hull. Remember, I said that Terzioğlu's theorem depends heavily on Schauder's theorem, T is compact if and only if T star is compact. So the people who work with the hypercyclic operator apparently spend a good quality time trying to understand when is both T and T star is together hypercyclic. But you see, this puts condition on X and X star, they both have to be separable if both T and T star is hypercyclic. So for example, L1 cannot support such an operator. And there are studies, there are other papers which which are along the lines that, okay, this space is admitting hypercyclic operators because this space has shrinking symmetric bases with hypercyclic adjoints. Okay, so this result that I am mentioning here, that the dual of injective hull is equal to the surjective hull, maybe gives a connection with the dual hypercyclicity of operators belonging either injective or surjective half. So it doesn't answer the question directly, but it places somewhere. It adds to its understanding. So what are the questions that one can ask? I just put here two questions. One is, how about other classes of operators? What is so special about weighted shifts? And I don't know the answer to this question. It did work for weighted shifts. And the reason why it did work for weighted shifts is the connection to the Q-compact operators. I'm not going to define what Q-compact operators are, but let me just say that they are genuine generalization of compact maps. They are compact with respect to a given approximation scheme. So there are examples of operators which are Q-compact but not compact because of the approximation scheme you have on your space. Well, so, when we were saying, okay, here are the typical LP spaces or the space of Rademacher, space spanned by Rademacher functions, which gives this type of operators. How about something else? And when trying other examples, we come across backward shift, and we were able to prove that backward shifts are Q-compact, but not compact, obviously. So there is certainly a relationship between degree of compactness that's going on here, which is not clear yet to my mind. Okay, so I'm running out of time, so let me tell you that the paper ideal of hypercyclic operators that factor through LP is going to come from Proceedings of AMS. The paper I wrote explaining the consequence of Terzioğlu theorem is published in Turkish Journal of Math. I think it's fair to mention Fourier here because he did work extensively about injective and surjective halves of classical P-compact operators. And I gave this reference before, but I put it in the list. So thank you for your patience and thank you for listening. I cannot thank you enough for your patience. And I don't know which language you accept my thanks, but this is my mother tongue. So teşekkür ederim.
Thanks a lot, Asuman, and teşekkür. Any question or comments for Asuman? And let me add that Asuman means sky.
In Persian.
Oh, well.
Or maybe in other languages too, I don't know.
Probably, yeah. So any question or comments? There is something in chat. Let me see. Oh, it's...
Since may I ask a question? You don't mind?
Go
Of
ahead,
course.
please.
Oh, hi. So, hi, Asuman, and thank you very much for a very nice talk. Can you maybe go back to the slide with the definition of your operator ideal?
Page 26.
Oh.
Okay. Well, maybe. So no,
Okay.
I guess it was after that. I'm sorry.
Yes.
And, no. Where you define your specific ideals as BN.
Okay. Backward nuclear.
Yeah. Backward nuclear. Exactly.
Yes.
Exactly. So, so I see here that you kind of define it with a built-in shift, kind of.
Yes.
But
yes.
is this built-in shift essential in the definition? So if we use yi instead of yi minus 1, will the definition be different or the same?
No, then it is different. Because compact nuclear operators are compact. And I wanted to, have a non-compact operator. So this gives the possibility of sticking backward shifts inside the factorization. But you are correct. This is a built-in construction.
Mhm.
And by taking AI as weak star and YI as weakly summable, so that's different too than an ordinary nuclear operator, right?
Right.
And realizing that these spaces can be identified with the spaces of bounded linear maps from either X to appropriate LP space or from appropriate LP space to X. And if you look at Terzioğlu's theorems proof, the way that he gets this closed subspace of C0 has some ideas of built-inness too. I know I'm answering your question in a vague way, but you are absolutely correct. I don't know who asked the question. I'd like to learn your name.
It's Timur.
It's Timur.
Oh, Timur, you are there. I see. Okay.
So my name means iron in Turkish, as we know.
Oh yeah, Timur. I mean, your name is one name that I can, pronounce easily.
Oh yeah. Yeah.
And
so
is Zahra's name. Zahra, I don't know if Zahra is a male or female.
It's a female from.
It's a female name in
Turkey.
Okay. Yeah. Well, yeah. My aunt was Zehra. So.
Yeah, Fatima or Zahra. They are same names. Yeah, she is working at Fields Institute, and I mean, a great help in the back of this focus program. I mean.
Oh yeah, I'm sure everybody is doing a lot because it's a very long program and it's running quite smoothly. This requires organization. Yeah.
Sure.
Timur, I'll send you the paper and then we can talk more if you like.
Yeah, definitely. Thank you very much. I'd appreciate this.
Okay.
Okay. Thank you again for a very nice talk.
Thank you, Timur. Thanks for your question.
Any further comment or question for Asuman?
Yeah, I have a question. It's maybe a naive question, but if you go back to the definition, the same definition, so it's maybe the same question, but I don't understand the answer. If you shift your y, your yi here, it doesn't belongs to LP prime weak.
No, it does.
It does. So
yeah, I'm all. Let me see. See, this is nuclear, right? Here, this is the ordinary nuclear, and here shifting yi. And putting weight, then maybe it's better to think about this. See, this is weak star summable. These are the prototypes of weak star summable. These canonical bases. Okay, in LQ prime, and this is in LP prime. So this becomes a backward nuclear WPQ backward nuclear operator.
Mm-hmm. Okay, thank you.
So there's too many indices. I'm sorry. This is, I was trying to make it clear, but I don't think I accomplished that. Too many indices, too many definitions, but this is what it is.
It's clear now, I think. Thank you.
Thanks.
Any further comment or questions? If not, let's thank Asuman again for her wonderful talk.
Thank you.
Thank you indeed. We resume tomorrow with Eva's colloquium talk at 11 Toronto time. So see you tomorrow.
All right.
Bye-bye.
Bye-bye.